All right. Hello, everybody. It's Arlington Matrix here. We're going to be taking a look today at some polynomial division. Now, for polynomial division, the general case, you have some function of x, we'll call it f of x, is equal to some polynomial p of x divided by quotient q of x. And so for polynomial division, we're trying to basically figure out what this evaluates to. So we can do that using long division. Long division would basically be, say for example, we want to do 1 divided by 3. We would do that as this symbol, 1. 3 goes into 1 0 times, move the decimal place, 3 goes into 10 3 times, minus 9 equals 1. So in this case it's 0.1. So we have a remainder 0.1, which means that 1 over 3 equals 0.3 plus 0.1 over 3, or 0.3 plus 1 over 30. And that's effectively what we're going to be doing here with polynomials instead of numbers. So as an example, if we have 2x to the 4 minus x cubed plus x squared minus x minus 1, and we're dividing this by x minus 1, what are we going to get? That's effectively what we're going to be taking a look at in this video. In addition, there's going to be some special cases and some examples towards the end of the video. See the description for the timestamps for those elements. So let's start this off by just doing the long division. So we wanted to divide that previous expression by x minus 1. So we have this long expression. We want to divide it by x minus 1. Why don't we just do the division? So x minus 1 goes into 2x to the 4 how many times? We can say that it goes into 2x to the 4 2x cubed times. So when we multiply 2x cubed by x minus 1, we're going to get minus 2x to the 4. We are also going to get minus, in this case plus, minus negative 1 times 2x cubed. And basically, we just follow the rules of long division as we would for numbers. The only difference is that we're using polynomials instead. 2x to the 4 minus 2x to the 4 is 0. X cubed plus 2x cubed is going to be x cubed. Bring down the next digit, plus x squared. And once again, we do this. X minus 1 goes into x cubed, x squared times 0 plus 2x squared. Once again, 2x and we see that this is plus 1 minus x plus 1, 0. So we see that this gives us a remainder of 0. So that tells us something very important. That means that if we were to do this division, this is equal to exactly 2x cubed plus x squared plus 2x plus 1. There is no remainder. Remainder equals 0. So this would be plus 0 if anything. So if we compare this to previously with our number example, first of all, we don't have a remainder. But this is effectively exactly the same. I'll do this in red. What we've just done is basically exactly the same as long division for numbers. The only difference is we've had a polynomial term in the numerator and the denominator. So what does this tell us? This tells us that x minus 1 is a factor of this initial expression, which means if we were able to factor out an x minus 1 and get an exact polynomial expression, then the initial polynomial expression must have had a factor of x minus 1. And indeed, if we multiply x minus 1 times 2x cubed plus x squared plus 2x plus 1, we will get our initial numerator, 2x to the 4 minus x cubed plus x squared minus x minus 1. So basically, what this has just given us is one of the roots of this polynomial. X minus 1 is a root of the polynomial, which means that at x equals 1, if we were to plot this on a set of coordinate axes, or on a graph, what this tells us is that at x equals 1, right here, is a root to the polynomial. It doesn't tell us what it does to the left or right. It could be going up, it could be going down. Let's just say it looks like that, for example. But this tells us a root of the polynomial. If we now take a look at what remains here, we can potentially try to solve the other roots of the polynomial. Unfortunately, that's not possible here, or it's not easy to do, because the other roots of the polynomial, one of them is negative 0.5, and the other roots are complex, plus or minus the complex root I. However, this tells us the root of x minus 1. So the whole point of this, if we were to simplify this polynomial further, we would just have x minus 1, we would have 2x plus 1, and then we would have the expression something like x squared plus 1. And this would be the fully factored polynomial expression, which would make it a little bit easier to analyze in terms of where the roots are located. So this is one of the applications of polynomial division. In the real world, polynomials are not quite so simple. It's a little bit more difficult to try and factor them. But in this particular example, we're able to factor it as such. Let's take a look at a few examples of polynomials that we can factor down. We're going to show some examples, and then I'll put some example problems at the end of the video. If you want to try them, solutions will be in the description. All right, so here's just a quick example. We're given the polynomial x cubed minus 12x squared plus 17x plus 30. We are asked to find the roots of the polynomial as well as to factor it. So factoring it would be in the form ... etc. So we can see that this is a third order polynomial. Since the polynomial is of an odd order, this means that we know there's going to be at least one real root. We can note that if it was even ordered, that there's no guaranteed roots. So in this case, we have an odd-ordered polynomial. We know that there's going to be at least one real root. So that's at least a little bit useful. We know that we should be able to solve, at least simplify this a little bit. So how do we determine which root to start with? So how do we determine kind of what our initial guess is for a root? So there's a few schools of thought on what we should try to divide by. But in general, what you'll want to do is make sure that it is a root of the polynomial by plugging it in. So we can basically take this 30, and we know that for the general form of a polynomial, we're going to have x plus a, x plus b, x plus c. A, b, and c could be positive or negative, but the end result is we're going to have something. We're going to have x cubed plus etc. plus a times b times c, which means that this 30 can likely be simplified down into its factors to find one of these factors of the polynomial. So if we have 30, we'll just list all the factors. 1 and 30 are factors of 30. So is 3, so is 5, so is 10. And these could all be positive or negative. So if we try one of these, we're going to try 3, positive 3. And if we plug that in, lo and behold, so we find that positive 3 is a factor of this polynomial. So now we can say that x minus 3 is a factor. So we can start factoring out this polynomial. All right, and we just basically, as before, we do the polynomial long division. So therefore, we've factored the polynomial. We know that x minus 3 was a factor. So therefore, the large polynomial equals, we see that we have a factor of 10. We could try factors plus minus 1, plus minus 5, plus minus 2, or we could just use the quadratic formula. And if we use the quadratic formula, that would be x equals negative b plus or minus the square root. And if we plug these into the quadratic formula, we get x equals positive 1 or 10. Sorry, that's negative 1 and positive 10. So therefore, x plus 1 and x minus 10 are factors. So therefore, and I'm running out of room at the bottom here, we can say that x cubed minus 12x squared plus 17x plus 30 is equal to x minus 3 times x plus 1 times x minus 10. And these are the factors. These are the three roots of this polynomial. So let's just plot this out quickly on a coordinate axis. So we know that x plus 1 is a factor. That means that the polynomial crosses down here. We know that x equals 10 is a factor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, somewhere up here. We know that it's going to cross there as well. We know that x equals 3, 1, 2, 3 is also a factor. If we consider the actual polynomial, looking at this polynomial, if we plug in x equals negative infinity, then we can see that this x cubed is going to dominate, and at x equals minus infinity, we'll call this f of x, goes towards negative infinity, which tells us that after this root, it's going down. Since this is a cubic, that also tells us that after this root, it must be going up, which also tells us that at this root, it's crossing something like that. If we go to use calculus, we can additionally calculate the points as well as the y-coordinates where the slope goes to 0, and we could potentially plot a curve. It might look like something like that. However, that's going to be for another video where we discuss calculus and curve sketching. But for now, we've factored the polynomial as was required, and we have the roots of the polynomial as well as a factored expression. Now, an additional note, which we will want to consider, is that we've only shown a polynomial, p of x, divided by some quotient q of x, where q of x is simple. This is not the case in general. We could have plus x minus 1, and we may have to solve that. It would be essentially the exact same x squared plus x minus 1, doing the exact same long division that we just did, x cubed plus 2x plus 1, and essentially saying x squared plus x plus 1, how much does that go into x cubed? That goes into x cubed x times, and you just have more variables to track. Minus x cubed minus x squared plus x. This will leave us with 0 minus x squared plus x plus 2x. That's going to be plus 3x plus 1. And then we have a remainder here, which we could try to factor further. We could say minus 1. So this would tell us that the expression up here equals x minus 1 plus 4x divided by x squared plus x minus 1. This expression doesn't tell us anything about the roots. This doesn't give us a root of the polynomial. It doesn't necessarily help our analysis. Now we have just a different quotient than what we had before. However, this does show that long division in terms of polynomials is not just restricted to simple polynomials. You may have to also divide by a more complex polynomial as well. As a final example, let's consider the case where we have an unknown within the polynomial. So we are given a polynomial of x to the 4 minus 6x cubed plus ax plus 2. and we are told that x equals 3 is a factor of this polynomial. We are asked to find the value of variable a. So how are we going to do this? Well, we know that x equals 3 is a factor, and we're given this polynomial. So we might as well just try dividing it and see what it gives us. So if we know that 3 is a factor, and that tells us we can divide this polynomial, and we should have no remainder. So x cubed could be plus 3x cubed minus 9x squared minus 9x squared. We're going to bring down ax. We have minus 9x, because x minus 3 goes into minus 9x squared, 9x times, plus ax, bring down that 2, plus 2. So we know that this should go into 27x minus 27 plus a times, because it's 27 a minus 27 x plus 3 a minus 27, which gives us equals 0 plus 2 plus 3 times a minus 27. So this tells us that we have a remainder that's dependent on variable a. We are told that x equals 3 is a factor, which means that this remainder r equals 0 if it is a factor, which means whatever a is must nullify this expression. So we can say that 2 plus 3 times a minus 27 equals 0, since x equals 3 is a factor. Therefore, we only need to solve for variable a, and we can do so directly. So we can say 2 minus 27 times 3, 81, equals negative 3a. Therefore, a equals negative 79 divided by negative 3 equals 79 over 3. So therefore, if we were to take this full f of x, we found a equals 79 over 3. And depending on how you want to represent that, you may simplify it further. You may represent it in perfect fraction form or in decimal form, however you want. But this is another application of polynomial division, and that is we're given this unknown factor. We know that we want x equals 3 to be a factor of the polynomial, so we simply solve for what this variable a is equal to. So here are some additional problems that you can try on your own. Problem number 1, fully factor the polynomials listed here. Purple indicates that it's a slightly more difficult problem than you would probably expect to encounter. And problem number 2, solve for the variable k. So where k is entered into the polynomial somewhere and you're given a factor, solve for what the variable k is equal to. And then a more difficult problem, we're given a polynomial, 6x cubed plus ax squared plus cx minus 5. It has a factor of x minus 1, so we're given that it has a factor. And when this polynomial is divided by x minus 1, it yields a remainder of 4. And we're asked to solve for the values a and c. Again, the answers to these problems will be given in the video description. However, I encourage that you solve each of these problems on your own before looking up the answer to check if you are correct. If you have any questions, please feel free to leave them in the comments section and I will happily answer. I'm Arlington Matrix. Thank you and have a good day.